Good day, I'm Maile Matsiba. Welcome back to our channel. Today we're beginning with semester test 2 of our CIR 123, which is the second chemical engineering module at the University of Pretoria. We're looking at the 2015 version of semester test 2, and we're looking at part 1 of that. It says that for the production of synthesis gas, which is a mixture of CO and H2, butanol and water are reacted. The fresh feed to the process contains 4% methanol on a mole basis, and butanol and water are in the correct stoichiometric ratio for the reaction. And there's a structure there. It goes further to say the reactor feed A contains 16% CH3OH on a mole basis. The methanol is in it, and the patch P is used to control the methanol in A. Stream D contains only CO and H2, and stream D contains no CO or H2. The conversion in the reactor is 10%. It says here that use a basis of 100 kilomole per hour of fresh feed F to calculate the following. So we have a couple of questions. At least we know that we need to use the basis of 100 kilomole per hour fresh feed F to calculate the question, to calculate the following questions. So the first question says calculate the mole composition of F. So we need to calculate the mole composition of F. And in F, we have been told the information that we have in F is that it contains 4% methanol, because they say the fresh feed to the process, which is the F here, contains 4% methanol on a mole basis. So already we know that in this fresh feed F, we have methanol, which is CH3OH as 4%. So let me just write here that basis 100 kilomole per hour fresh feed F, right? So that is basically the basis that we're going to be using. And with that said, we already know that methanol, which is CH3OH, is equals to 100 kilomole per hour multiplied by 0.04, which is the mole fraction of methanol. So that becomes 4 kilomole. So in the feed F, in the fresh feed F, we know methanol is actually 4 kilomole when we use a basis of 100 kilomole per hour, because it's 4%. So now, out of the 100%, or rather out of the 100 kilomole per hour, we know methanol is 4%. So that means that the remainder of the 96 kilomole is actually C4H10O0 and H2O. So we know that both these two, butanol and water, together make up 96 kilomole per hour. But we don't really know how much is exactly water and butanol individually. However, we can use that. There's some information that we are given. We are told that butanol and water are in the correct stoichiometric ratio for the reaction. So which means that we can just look at the reaction equation and know that, well, for every one mole of butanol, there's 3 mole of water. So which means that there's a total in the 96 kilomole, there's total of 4 kilomole, or rather I can just say, for ratio purpose, I can say out of 4 moles, one mole is C4H10 and 3 mole is H2O. And with that said, we can just say C4H10 0 is equals to 96 kilomole per hour multiplied by 1/4, because we know that for every 1 mole of butanol, there's 3 mole of water in the 96 kilomole. And with that said, if you use your calculator, that will give you 24 kilomole per hour of butanol. And with water, you can do the same and say H2O is equals to 96 kilomole per hour multiplied by 3/4, because there's 3 mole of water per 1 mole of butanol. So when you use your calculator there, it's going to give you 72 kilomole per hour. So now The question says that calculate the mole composition, or let me say the mole percent. The actual question is actually requesting the mole percent composition. So they say calculate the mole percent composition of stream F. And if we have all the information here, we can just say, therefore, percentage composition, right, of F. We know that this one we are told that methanol, we are told that it's 4%, and we know that butanol, we just calculated it to be 24%, and we know that H2O is equals to 72%. So with that said, that actually wraps up question A of the question. Now this takes us to question B. So in B they say calculate the mole fraction of methanol in R. Now let me bring back the diagram here. This is R here. What they want is that they want us to calculate the mole fraction of methanol in here. So if you look at R, it's actually it's a recycled stream after it went through after the stream went through A, B, and there was a separator, and part of it was patched, and then R. So for us to easily understand, or to easily find the analysis of R, it's important that we can just take it step by step, analyze A, analyze B, analyze D, and then we'll get to R. Actually, if you can look at the diagram, if we can get the mole fraction of methanol in D, that is actually the mole fraction of methanol in R and P. This is because if you look at here, this is actually the same stream. They just patched part of it and recycled part of it. So there isn't really much change in the properties of the stream. They just patched part of it and kept part of it exactly as it is. So if we can be able to find the composition of D, then we'll be able to find the composition of R, and then we'll find the methanol in R. So now going to the question, this one is a little bit longer, but I tried to make it a little bit more understandable. So let's start in stream A. Let me say in stream A, this is stream A here, right? In stream A, we know that methanol, we are told that methanol CH3OH is equals to 16%, right? So the methanol here is 16%. We are told here, it's the information that we are given, that the reactor feed A contains 16% methanol. Now, another important element that we need to, okay, I'll get to that one. Let me just put here and explain that butanol, which is C4H10, right, 0 plus H2O, right, together combined, they are equal to 84%. And let me just explain that. If this is 100%, and we know for sure that stream A contains C4H10, 0, H2O, and CH3, then that means that the remainder of the 84% is actually the butanol and the water, because we've already been told that the methanol is actually 16%. And another important thing is, if you can look at stream A, it's actually stream F plus stream R. So stream R would have been problematic if the separator wasn't really perfect separation. But we are told here, if you can read, we are told that stream E contains only CO and H2O, which means in E there is no butanol or water or methanol. And also they say that stream D contains no CO and H2O, which means from the reaction equation, from the reactor, all the CO and H2 did separate there. You see, so in here there's no CO or H2. That is important, because that means that the properties, or how do I put it? That means that in R there's methanol, there's butanol, there's H2O, and there's also methanol. And also in F there's the same compounds, and also in A there's the same compounds. So that kind of, in a way, well, that helps us jump the first hurdle. And the second important information, which is actually the core to this question or even this part of the semester test, is to understand that if R, if F is in the same stoichiometric if R is in the correct stoichiometric ratio, and also if F is in the same stoichiometric ratio and R is in the same stoichiometric ratio, then also A is in the same stoichiometric ratio. So it might be a little bit not so easy to find or discover that, or to realize that R is actually in the same stoichiometric ratio, especially when you look at butanol and H2O, right? But you can easily detect that when you look at the separator here, that all the CO and H2 went there and everything else went here. And remember, if in A, remember that if it was in the same stoichiometric ratio, it entered here. And how do I put that? If all of the F was in the same stoichiometric ratio and it went through A, in the reactor, when it got consumed, it also got consumed in the same stoichiometric ratio. So which means throughout the process, there's not really a point or a time where butanol and water are no longer in the same stoichiometric ratio. So everywhere in the process, butanol and water are in the same stoichiometric ratio. If one would have attempted that, if for one to change that, something would have happened in the separator. Maybe find a way of, for example, if I just for understanding purposes, maybe find a way of evaporating part of the water and leaving the butanol, like tamper with that. But as it stands in the separator here, or everything, or in the separator, nothing really much happens to that has a potential of changing the fact that butanol and water are in the same stoichiometric ratio. And with that said, the whole process, butanol and water are in the same stoichiometric ratio. And lastly, on that one, I need to emphasize this. It's important to understand that the masses or the amounts in the moles may change. You see, A and R are not the same, and P and D and B and F, right? But the ratios of butanol and water are always in the same stoichiometric ratio. So it doesn't matter how big R is or how small it is or how A is, whatever happens, but whichever way they are, butanol and water are in the same stoichiometric ratio. This is actually, this concept I've just explained here and emphasized is the crux of this question. If you miss this one, then the question takes a different approach. Like it really goes in, you can never solve that, you see. So thank you for that. So now coming back, or let me just write it down that, let me just write here that, okay, sorry. Let me just write here that, butanol, which is H10O, and H2O are in the correct stoichiometric ratios in F and also in R, right? And thus also in A. So I just explained that if they are in, if the stoichiometric ratio is the same in F and R, then it must be the same in A. Yeah. So now moving on from here, remember that we've already established that butanol and water is 84%. Now we want to know, out of the 84%, how much is the percentage of butanol and how much is the percentage of water? And we will go back to our chemical reaction equation and use this concept I've explained here of the stoichiometric ratio. So we can just say, therefore, C4H10O, right, is equal to 1 over 4 multiplied by 84%. And If you use your calculator, it gives you 21%, right? And H2O is equals to 3/4 multiplied by 84%. And if you use your calculator, it gives you 63%. So with that said, now we know that in A we have 16% methanol, and we know that we have 21% butanol, and we have 63% water. Yeah, so now this is actually the first part of B. Now moving forward, now we need to remember we are actually going to R, but we're going process by process. So we need now to analyze B. But for us to analyze B, remember we only know the composition of A, but we don't know how much is A. If we knew how much is A, then the problem would have been solved. It would really take 2-3 lines and it would be done. But now we don't know how much is A, right? But we know the composition. We know the analysis that it's 16%, 21%, and 63%. So it's important, or I found it wise to actually define A into X. So let's just say, let X be the number of moles of the reactor feed A, right? So what I actually did was I decided to define this as the number of moles of feed A as X. The reason for that is that I want to analyze B, right? But I don't know how much is A. So I'm going to be analyzing B in terms of A. But because I put it in X, my B is going to be expressed in terms of X, right? And that is actually going to help me as I move forward. So therefore, let's start with the methanol. CH3OH is equals to 0.16x, right? Remember, it's 16%. So, and then the butanol C4H10 0 is equals to 0.21x, right? It's it's 21%, and yeah, these are mole fractions multiplied by the total. So H2O is equals to 0.63x. So now I have now I have the number of moles of methanol, butanol, and H2O in A in terms of X, right? And if I have the number of moles of A, if I have the analysis of A and the number of moles of each in terms of X, then I can easily analyze B. Because remember, I have the information of the reactor. I'm being told that the conversion in the reactor is 10%. And also I've been told that the methanol rather, it's actually inert. Where is it? Yeah, we have been told that the methanol is inert, which means the methanol won't really react. It won't tamper with the equation. It won't change in any way. So then let me say, therefore stream D composition, right? In stream decomposition, the first thing that we know is methanol. CH3OH is equals to how much? 0.16x, right? Why is it 0.16x? It's inert and it doesn't really change. Now I go to the butanol, C4H10, right? 0 is equals to, remember I'm being told that the conversion in the reactor is 10%. So that means that out of the total, the butanol, out of the total of 0.21x, which is the amount of moles of butanol, 10% of it is going to react and 90% of it is going to be left. So with that said, I can just say the total, which is 0.21x minus the total 0.21x times 0.1, this is the 10% that reacts, right, is equals to, right, 0.21x minus 0.02 1x, right? And is equals to 0.189x. Now, this is actually the butanol that is left in B. So already I've established that in B, there's actually methanol, which is 0.16x, and butanol is 0.189x. Then I need to get the water and all the other compounds, right? Then going to water and doing the same, H2O, right, is equal to 0.63x minus 0.63x multiplied by 0.1 is equal to 0.63x multiplied minus 0.063x, right? And is, if you use your calculator, it gives you 0.567x. Let me just write here that 10% reactor conversion, right? And also let me write this one here. That this is a reason that is 10% reactor conversion, right? So now, where's the diagram? Looking at the diagram, we already know in B that we have we know the methanol, we know the butanol, and then we know the water, right? And now it's not only that. Remember, this is a reactor, which means in B now there are new guys. There's the CO and the H2. So now we need to find a way of calculating how much is CO and how much is H2 that is actually formed as a result of the reaction in the reactor. And for us to get that, we can just use butanol. It's easy. You can also use the water, but because of the one coefficient of butanol here, it's always easier to use it. So I'm going to use butanol. And let me just write here that butanol C4H10 reacted, right, is equals to how much? Is 0.21x multiplied by 0.1 is equal to 0.021x. So this is the butanol that reacted, right? And according to the equation, the ratio of butanol and CO is 1:4. So if I know how much butanol reacted, I can then calculate how much of CO formed. So let me just write here that the ratio of C4H10 and CO is 1:4. Therefore, CO formed is equals to what is reacted, which is 0.021x multiplied by 4, right? And if you use your calculator, it should give you 0.084, right, x, right? That is actually the CO that is formed. Now going back, now we then need to go back to the hydrogen. So we can just say the ratio of C4H10O and H2 is 1:8. Therefore, H2 formed is equals to what is reacted, which is 0.021x multiplied by 8, right? And if you use your calculator, that should give you 0.168x, right? So now we have actually concluded, we have actually analyzed, we know the amount of each of the compounds in B, but in terms of X, right? So we know methanol, butanol, water, CO, and H2. So with that said, then we can actually move further to analyze stream D. So then we can just say stream decomposition. Stream decomposition, right? Now in stream D, I need to explain something. In stream D, there's a separator, right? Everything that is in B doesn't really react here. What happens is all of the CO and H2 separate and go to E in the stream E, and everything else, which is the methanol, butanol, and water, go to D. That means that in D, what's happening in D is that it's actually what is in stream B, just excluding CO and H2. So we'll just copy that. We'll just say then in stream decomposition, let's start with the H2O. H2O is equals to, it hasn't changed, it's still 0.567x, right? This is it. And methanol, CH3, CH3OH. The methanol is 0.16x, right? And the butanol, CH4H10O, is equals to what's the butanol? The butanol is 0.189x. So this is basically stream decomposition. So it's just a repetition of B, but without CO and H2 because there was a separation there. Now, if we have that, remember, now that we are in D, we can actually calculate the percentages because we see that everything, the percentage composition of D is the percentage composition of R and also of P. So for us to do that, let's say total stream D is equals to 0.567x plus 0.16x plus 0.189x, right? And if you use your calculator, that is going to give you 0.916x. See, so now with that said, if we're able to calculate that, we can just say we can now go to the percentage composition. So let's just now say, remember initially we had the composition of D, just how much of each that, but now we need the percentage composition of D. So percentage composition of stream D, that, right? So we say percentage methanol OH is equals to 0.16x all over the total, which is 0.916x multiplied by 100%. And if you use your calculator, it gives you 17.4672%, right? And then the percentage of butanol, which is C4H10O, is equals to 0.189x all over 0.916x multiplied by 100%, right? And if you use your calculator, it gives you 20.6332%, right? And then the percentage water, percentage H2O is equals to 0.567x all over 0.916x multiplied by 100%. And if you use your calculator, it gives you 61.90%. So this is actually now the percentage composition of stream D. Now with that said, we can just say we know we know that the percentage composition of stream D is equals to the percentage composition of stream R, right? This is basically because we know here there's not really much that is happening. So in here there's not much change. It's just that a portion of the D has been patched. So the percentage composition doesn't really be affected by that. And with that said, then we can go further to say, therefore, the mole fraction of CH3OH in D is equals to the mole fraction of CH3OH in R, right? And that is equals to 17.4672% all over 100%. And if you use your calculator, it gives you 0.174672. So this then becomes, remember our question was saying, calculate, where is it? They wanted the mole fraction of CH3OH in R. And yeah, this is it here. The question was saying, calculate the mole fraction of CH3OH in R. And if we're able to calculate that, then this means that we have actually concluded our question B of this semester test. So thank you for your time, and I hope we meet again in our next video.